A very warm welcome to all of you in this lecture on processing of polymer matrix composites. As you are well aware that we are discussing a series of lectures on processing of non-metals. In this series, we are now focusing on module number 5, which is based on polymer matrix composites and the processing techniques and methods for polymer matrix composites. In this module, we have already taken 2 lectures. In lecture 1, we have seen the challenge for selection of materials and the importance of composite materials in today's world. We have seen that how new materials are required in today's scenario. If you remember, we have seen that there are design modifications as well as there are in-service requirements which leads to the needs and requirements of new and new materials which can satisfy these design requirements as well as the in-service requirements. We have also seen that why the new materials are needed and how the new materials are developed. We have seen that internal modifications or internal changes in the structure of the material and the external changes in the form of reinforcements added to the materials lead to the development of new materials. As new and new materials are getting developed, we need to develop cost effective high quality manufacturing techniques or processing techniques for these materials. In the first lecture, we have seen that when there are variety of materials available with us, we need to select the most optimal material for that particular application for which we are thinking to design. In lecture number 2, we have seen the classification of composite materials. We have seen that how the composite materials can be classified. What are the various application areas of different types of composite materials? If you remember, we have finished the lecture with 3 important classes of composite materials, that is the polymer matrix composites, the ceramic matrix composites and the metal matrix composites. I have highlighted that in these series of lectures on processing of non-metals, our focus would primarily be on ceramic matrix composites and the polymer matrix composites, and this particular module is dictated or is dedicated towards polymer matrix composites and their processing techniques. So, today we will discuss the challenges and the issues as well as the basic constituents that go into the manufacturing or processing of polymer matrix composites. Now, what are the constituents of polymer matrix composites? With PMCs, as we have already seen in the previous lectures, PMCs means polymer matrix composites. So, the matrix is a polymer and the reinforcement is in the form of the fibers. You can see on your screen very clearly it is mentioned that there is a fibrous reinforcement, fiber filament reinforcement, and the matrix is in the form of a polymer. This is one representation of a polymer and you have a fibrous reinforcement, and when both of these constituents combine together, they lead to a composite. This is a composite. There are different layers. This is layer number 1 of the composite, this is layer number 2 of the composite. If you remember, in the previous class also we have seen that how a composite looks like. Again, I would like to revise that how a composite laminate would look like. You can see on your screen how a composite laminate would look like. Here you can see this is a composite laminate, suppose. Now, these lines represent the different layers. So, how many layers are there? Layer number 1, 2 and 3. So, there are 3 layers. So, usually we make symmetric laminates, we will have 4 layers. In this direction also there will be 4 layers. So, this is, we can say, is a composite laminate. Now, in this composite laminate there are 2 ingredients, that is there can be fibers and there can be reinforcement. So we can have fibers and there would be matrix plus matrix. So we have fibers plus matrix which will add up into a composite material. So on your screen in the slide you can see that there are fibers as well as there is a matrix. As you can see on your screen, you have the fibers and the matrix. So fibers and the matrix, they add up to make this particular composite, which we have just, I have drawn one diagram of a composite laminate. In that laminate there are fibers in this particular form and there is a matrix in you can say semi-liquid form, in a semi-solid form, and when these two things are combined together we get a composite plate. So here you can see different types of colored composite plates. So basically the constituents that go into the fabrication or processing of a polymer matrix composites are two major constituents. The two major constituents are the fibrous reinforcement and the polymer matrix. The matrix would always be in the form of a polymer. Polymer can be of different types, maybe it can be a thermoplastic, it can be a thermoset. The fibrous reinforcement could also be of different type, that we will see in the subsequent slides, that what type of fibrous reinforcement will go into making a polymer matrix composite. So there is a diagram which explains on the basis of reinforcement how the composites are named. It is a very big family of polymer matrix composites. So depending upon the type of reinforcement that we are putting in or the shape of the reinforcement, there would be different types of polymer matrix composites. But one thing for all of you to remember is that when we are talking of a polymer matrix composite, there are two things that should always be kept in mind, that the matrix would always be a polymer and the reinforcement would always be in the term of a fibrous material. Now fibrous material can be continuous or discontinuous, it can be aligned in one particular direction or it can be randomly oriented. So all these things we are going to see in today's lecture. Now here again on your screen you can see there is a very simple diagram in which we can see these round circular cylinders are fibers in this particular direction, and these are again they have been classified as reinforcing fibers. So these long cylinders inside this particular cuboid are reinforcing fibers and the rest material is filled with the matrix. So we have fibers in this particular direction only and we have matrix which is encapsulating these fibers. So we have this modulus of elasticity in longitudinal direction and in the transverse direction also. So we can see that there are reinforcing fibers and there is a matrix. So this is, you can say, one simple representation of a polymer matrix composites in which we have reinforcing fibers and a bulk of the matrix. So the matrix is in the form of a polymer which has been reinforced with the fibers. Now these fibers can be of different materials that we will see in the subsequent slides. So here on the stress strain plot you can see this is a stress strain behavior of a matrix and this is a stress strain behavior of a fiber. So the stress strain behavior of a composite is lying in between the stress strain curve for the matrix and the fiber. So this clearly outlines one of the important aspects that which we have already seen in the previous slides or in the previous lectures, that the properties of the composite should be a combination of the properties of the matrix and the reinforcement. So here we can see the stress strain behavior of a composite is made up by the stress strain behavior of the matrix and the stress strain behavior of the fiber. So it can be very easily understood that when we are combining two different macro constituents together to make a composite material, the properties of the composite would be dictated by the properties of the two macro constituents, and sometimes it is also possible to attain those properties which are not possible with the individual constituents alone. So this particular diagram shows, it represents physically how the reinforcing fibers are used to reinforce the polymer matrix, and then we have properties which are different in x, y and z direction. And here with the stress strain curve we can very easily see that the composite represents the both the macro constituents. The constituents are the fiber and the matrix. Now, what are the properties of the PMCs? As in the previous slide we have seen, the properties are dependent upon the properties of the fiber and the property of the matrix. So, here we can see on your screen, overall the properties of the polymer matrix composites are determined by the properties of the fiber, the properties of the resin, the ratio of fiber to resin in the composite, which is called as the fiber volume fraction, the geometry and the orientation of the fibers in the composite. So, on this screen it is just a continuation of what we have discussed on the previous slide. As we have seen, the property stress strain behavior of the composite is dependent upon the stress strain behavior of the matrix and the stress strain behavior of the fiber, or in other language we can see it is governed by the stress strain behavior of the matrix and the fibers, and it lies in between the behavior, in between the two characteristic curves. So, the same thing has been put into words in this particular slide, where we can see that the properties of polymer matrix composites are dependent upon the properties of the fiber, the properties of the resin and the ratio of the fiber to the resin. So, when we are combining the two macro constituents, the decision is in our hands. We have to take a decision how much fiber we have to add and how much matrix we have to add. Sometimes the fiber volume fraction may be 20% and the bulk of the material, that is matrix, can be 80%. On the other hand, we can have fibers up to 50% and the resin or the matrix can also be 50%, that is fibers 50%, polymer 50% combined together to make a composite. So, the decision lies with us, and the properties of the polymer matrix composites are dependent upon the amount of fibrous reinforcement we have put into the polymer matrix. The last point, the geometry and the orientation of the fibers in the composite. So, if all the fibers are aligned in one particular direction, the properties would be different. If the fibers are randomly oriented, they are distributed randomly in the bulk, that is distributed randomly in the polymer matrix, the properties would be different. Now, depending upon the requirement, we will see whether we want to use a randomly oriented composite or we want to use a aligned fibrous reinforcement in the composite, whether we need to have a continuous reinforcement or we can have a discontinuous but aligned reinforcement. So, the reinforcement can be added in the polymer matrix in a number of ways. So, that we will see in the subsequent slide with the help of a diagram, that how the different types of composites are made with the help of different types of reinforcements being put into the polymer matrix. Now, this gives just a very I should say simplistic view of the comparison between the steel and the composites. On your left hand side you can see we have steel and the composites. Now, steel, we can say it has low material cost. I will just read out some of the characteristics of steel. It has low material cost, high installed cost, it can be corrosive, it is heavy, fabrication is required if we want to make a composite structure, different types of fabrication. If we want to make a steel structure, different types of fabrication are required, sometimes welding may be required to join the two steel members together, and the maintenance costs are usually high for steel. So, these are some of the important points in context of steel. Coming on to the composites, I will just read out for you. Composites in the very beginning have high material cost, they have low installed cost, they are non-corrosive in nature, light in weight, no fabrication is required and low maintenance costs. So, we can see that for any structural member, if we are comparing the two materials out of which we can choose our material, composites usually give us a better alternative as compared to steel. But yes, in some specific instances or some specific requirements, steel may even be better than the composites. For example, the composites have a huge disadvantage in terms where the temperatures are very high, because the polymer may be able to sustain a temperature to a particular level only, whereas steel can sustain a very high temperature. So there are few areas where steel still has got a lot of advantage over composites, but these points have been highlighted where composites have an edge over the steel. Here in this particular case, let us take the last particular point, that is high maintenance in case of steel and low maintenance in case of composites. So suppose we have a underwater application and we have used a steel structure underwater. So always there is a corrosive environment underwater. So steel may require frequent painting in order to, or frequent coating on the surface in order to avoid that corrosive environment. Whereas if we are using a composite structure underwater, as it is non-corrosive, or it can be made non-corrosive, as we have already seen in the previous lectures on this particular module, that we can add some pigments or we can add some additives in the polymer composites to make them non-corrosive. So if we have made a composite which is non-corrosive, we have tailored the properties of the composite in order to make it non-corrosive, then this particular composite can challenge even steel in underwater application. So each and every point which has been mentioned as a comparative point between steel and a composite can be explained with the help of examples. For example, we can take point number 4, that is steel is heavy and the composites are lightweight. As we have seen in the previous lecture, composites have a very good mechanical property of strength to weight ratio. So composites are light in weight. If we have aerospace applications, in aerospace application the first and foremost criteria is lightweight. So the composites have an edge over steel in aerospace application. So because they may provide the same strength but at a relatively lower weight. So each and every point can be explained with the help of examples. So in these particular comparison, we can just have an idea that composites have got some specific applications in engineering structures. So wherever steel is being used, it can be in certain circumstances be changed by the composite materials, or the composite materials can be used for replacing conventional materials like steel and other structural materials. Now what are the challenges in context of materials? So we have just seen one comparison, which is a very simple comparison between steel and a composite material. Now we are just going to see that what are the challenges among different materials. Our focus would be to just highlight the use of composite materials in certain engineering applications. So we would be focusing on the applications and the specific properties of composites and how they are being challenged by the conventional materials. So on your screen you can see the very first point, challenge from the technical innovation in metals. If we propose the use of a composite material, there is some innovation in the field of metals also. Suppose we say that composites are most suitable or most suited for the low weight applications. There may be some innovations in metals which are light in weight, or there may be developments of some alloys which are light in weight. So there is a competition between the composites and the metals industry. So for lightweight applications also we have composites, but we have some alloys and metals also which can challenge the applicability of polymer composites in lightweight application. Coming on to point number 2, on your screen you can see misconception about the durability of plastic products. Sometimes we feel, it is in our mindset that if it is a metal, it is going to be very strong, tough, hard. This is a layman's terminology for any metal. If we say how would you compare a metal and a plastic, the person would always give thumbs up approach for the metals. Why? Because there is a general conception that metals are strong, they are tough, and the durability of plastic products is always questionable. So there is have to be a justification that yes, plastics are equally or even more durable than the metals. The third point, combustion and smoke liberation characteristics. Whenever we will propose the use of a polymer matrix composite, one of the doubts in the user's mind would be the combustion and the smoke liberation characteristics, that it can catch fire, it can be flammable in nature. So combustion and smoke liberation characteristics is another challenge which has to be addressed when we are talking of use of composites in everyday applications. Fourth point, long term durability and fatigue characteristics. Long term durability means the metals have been in use for a very long period of time. We can see metallic structures all around us, and the durability characteristics are already established for metals. Suppose I take a particular alloy and I want to design a structure with that particular alloy. I have the historical data available with me that this particular alloy under these particular operating conditions or in service conditions should be able to sustain this much period of life or this much period of reliable life, or we can set the life of a particular structure if we know the long term durability data for that particular material which is going to make that structure. But in case of composites, which are materials which are not having life more than 4 decades, mostly the composites, these polymer matrix composites have been developed in 1970s specifically for aerospace applications. So the long term durability data for composite materials is not yet available. So when it is not available, there is always a doubt among the designers that how these materials are going to behave for a longer period of time. But yes, these days there are accelerated testing mechanisms to find out that how the material will behave under certain set of conditions. So long term durability and fatigue characteristics are also important when we are proposing the use of a composite material for a particular application. Failure mechanisms of laminates and composite structural systems. So failure mechanisms of laminate means that for a metal, everybody knows, anybody who has studied engineering, that if a load is acting on a material, how then the material is a metal, how it is going to fail. Whereas in case of composites, it is not clearly understood because the composites have anisotropy, the properties are different in x, y and z direction. So when you are loading the material in one particular direction, what is going to happen in the other directions, that is not well understood. Yes, the work is progressing in that particular direction, but still the actual failure mechanism have to be established for composite materials. Then approved industry design codes and common repair system. Till now the composites are being developed, so the standards have to be developed for the design as well as for the fabrication of composite materials. So that standardization process is still going on, and because the family is too wide, different types of fibers can be used to reinforce different types of matrices or different types of polymers. So the standards that have been set for one particular family have to be adjusted for the other particular family. So this particular slide highlights on the challenges that the composites face from its counterparts or from the conventional materials. So if I just read the slides, this particular points on this particular slide from the metals perspective, we can see I have just read this slide from the perspective of composite materials, that what are the issues and challenges in context of composite materials. If I see what are the advantages in terms of the metals in this particular slide, we can see first challenge from the technical innovation in metal. In metals industry, the focus is on developing low weight metals or lightweight metals. Misconception about the durability of plastic products. The durability of metal products is already well established. Combustion and smoke liberation characteristics is not an issue with the metals. Long term durability and fatigue characteristics data for metals is already available when it is exposed to different loading and operating environments. Failure mechanisms for metals are easily understood and well established and properly recorded in the design data books, and there are approved standard design codes for metals, and there are proper repair systems for the metals. So for metals industry, which is in particular use for such a long time, for metals lot many things have been established. Whereas in case of composite materials, many things are in the process of establishment and few things have already been established. So there are few challenges for composites from the metals industry. But there are new and new applications for polymer matrix composites that we are seeing in our everyday lives. So, this particular slide and the previous slide gives a comparison between the metal and a polymer composite, and it highlights that what are the challenges for the polymer composite in context of the things or the characteristics or the properties which have already been established for metals. For metals we have a full design data books. For composites the process is going on, and it is not too far that when we will be having a complete design guidelines, a complete fabrication guidelines, a complete data book for composites also, in which can be used for different types of fibers, different types of matrices, different types of additives and different types of processing procedures. So, the process is on, and it is not too far away time when we will be able to see that the things which we are seeing established in terms of metals would also be established in terms of polymer composites. Then there are few challenges in general nature. Those were the technical challenges which are there. Now there are few challenges which are general in nature. For example, the cost justification. Processing methods developed for aerospace industry. Cost justification, let me just first highlight the cost justification. If you remember a slide on the comparison between steel and a composite, steel was, the initial cost was low, or the cost for steel is lower as compared to the cost of the composite material. So, whenever we are proposing the use of a composite material, we have to emphasize that how we were going to justify the escalation in the cost, or how we are going to justify the high cost of the composite material in comparison to the lower cost of the conventional material such as steel. So, there are two important points which can be highlighted to justify the cost. First important point is the processing methods which are used for fabricating or processing the composite materials were developed for the aerospace industry. As I have already highlighted in today's lecture that the composite materials, specifically the polymer matrix composite materials, were developed for the aerospace industry in the 1970s. So, when these were developed for the aerospace industry, the processing techniques or the methods that were used were also developed for the quality constraints or the quality requirements of the aerospace industry. These particular day, in today's scenario, the composites are finding application in household items also, in automotive industry also, in marine industry also, and the processing techniques that were developed are still the same or nearly the same which were developed for the aerospace industry. So, the quality constraints are quite stringent in aerospace industry, but they are quite relaxed in household application. So, when we are making a component for our household application, we can use a different processing technique which is not so quality conscious. We can slightly compromise with the quality when the product has to be used in any simplistic household application. So, the processing techniques which were developed for aerospace application have to be modified so that they become cost effective and they may be able to produce a particular product for household application at a lower overall cost. So, the need of the hour is to develop certain processing techniques which are not very costly. The second important cost justification is the lowest cost bid accepted, and no importance is given to the life cycle cost. So, as we are going to procure a particular material, we would be just looking at the lowest cost. We would not be taking the life cycle cost into picture. Usually this is a trend. So, when the composites have high initial cost, people are not going to accept the composite in place of any conventional material. But if we see the life cycle cost, if you remember the slide on the comparison between the steel and the composite material, one of the points was maintenance. In case of steel, suppose I have given the example of underwater application, frequent maintenance is required, whereas in case of composite materials the maintenance requirements are less, which leads to a lower life cycle cost of a composite material as compared to a high life cycle cost of any conventional material. So, if we only focus on the lowest bid, we would never be able to propose the use of a composite material. So, these 2 points if taken into account, the 2 points being the processing technique should be reinvented to suit the needs and the requirements of the low end applications, and the lowest life cycle cost material should be chosen, and only at the first instance the lowest cost or the lowest cost bid should not be taken into account. The life cycle costing should always be used as a criteria to select a particular material for a particular application. So, cost justification is another issue that should be go in favor of the composite material. Then the standardization issues, standards not followed in specifically in Indian scenario. So, there are, this may be a scenario some 10 years back, but today there are lot of standards which have been developed, and the composite industry has seen lot many changes over the last 5 to 10 years. But at the very beginning there were few issues and challenges in context of the standardization, but today I can very emphatically put this point that lot of standards have been developed and all the standards are in place, but still there is an inhibition that there are few issues which are related to waste disposal, there are few issues related to recycling, and finally the resistance to change. Again, to emphasize these challenges of general nature, cost justification, yes, it can be done. Standardized issues have already been settled, there are already industry standard codes which are now in practice. Waste disposal, recycling and resistance to change are 3 issues which still require approval from the composites fraternity or from the engineering fraternity at large. Composites fraternity or the composites people would always propose the use of the composite material, whereas there are few challenges in terms of resistance to change. Always when a new thing, a new particular material or a new processing technique or a new method of doing a job would be proposed, there would always be a resistance to change. So, if we propose the use of a composite material for a particular application, always there would be a resistance to change, because that particular application is in place for so many years and the conventional materials have been used to make that product. Now, if I tell the industry to change the material from its conventional material to an advanced material like a composite, they may have that resistance to change. Although when we propose, we have all the standards in place. With all those standards we go and we propose the use of a composite, but still there is a resistance to change. So, a change management is required, and there is a complete branch of management which is change management, which can be used, or the principles of that particular method can be used to change the mindset of the people. So, there are challenges for polymer matrix composites. So, just to summarize, there are few technical challenges, there are few challenges which are general in nature. In the previous slide we have seen the challenges in context of materials which are technical in nature. In the second slide we have seen the challenges which are general in nature. So, in general nature, cost justification can be done, standardized issues have been settled, yes, the work is going on in waste disposal, recycling and resistance to change. Now, coming on to the challenges in the primary processing. So, when we are talking of a particular module, we are seeing in this particular module we have to cover the processing of polymer matrix composites. So, there are 2 important things, the polymer matrix composites and the processing. We have till now seen the materials aspect of polymer matrix composite. What are these materials? What are the macro constituents? What are the specific advantages? What are the specific challenges these materials have in context of or in comparison to metals? Now, we will see when we have to process them, then what are the challenges. Now, we know what is a polymer matrix composite, what are the ingredients that go into the polymer matrix composite, that we have already understood, that there is a fibrous reinforcement, there is a polymeric matrix. We have to combine these 2 things together to make a composite material. When the composite is made, how it can challenge the conventional materials, or what are the advantages and limitations or the important properties of the conventional materials, what are the you can say application areas, properties of the polymer matrix composite, in which particular areas the polymer matrix composites can challenge the conventional materials, and what are the limitations of polymer matrix composites. As one example I have given as the high temperature applications, which is one of the important limitations of polymer matrix composites. So, from the materials aspect, I think we have developed adequate knowledge which is required to go now towards the processing of these materials. Now, what are the challenges in processing of polymer matrix composites? We would focus on these points. Let us see the point number 1, tailor made, which we have already seen, that depending upon the design requirement we can choose which type of fiber, whether it would be a continuous or a discontinuous fiber, whether it would be aligned or it would be randomly oriented. We can take some decision in terms of fiber, we can take some decision in terms of the polymer matrix, it can be thermoset, it can be thermoplastic, what type of additives are required to be added. So, we can design our material, we can make a polymer matrix composite depending upon the requirement or the design requirement or the in-service requirement. But the major challenge is that how to blend these two parts together or two macro constituents together or the two constituents together in order to design and develop a composite material. So, yes, these materials have the property of tailorability, we can design our materials, but the property poses most perplexing challenges in processing. So, there are few challenges in the processing that are there because there are so many types of fibers available, there are so many types of matrices available, and when we have to combine them together, one particular process cannot be used. So, tailorability of the polymer matrix composites, till now we understand it is an advantage, but how to incorporate this tailorability into processing, that is one of the biggest challenge. Second point, how to blend two different materials having substantially different mechanical and chemical properties. Now, fibrous reinforcement has got its own mechanical and physical and chemical properties. The matrix has got its own mechanical, physical and chemical properties. Now, there are two materials or two constituents which have different properties, and we have to blend them together in order to make a new material which we are calling as a composite material. So, this is another challenge, because the properties are different, the techniques have to have that generability in nature that they are able to blend these two things together. If we suppose we are going to heat and blend the two things together, the melting point of fiber would be different, the melting point of matrix would be different. So, we have to take into account that which process can be used to blend these two things together. So, the first challenge is the tailorability. The second challenge is the difference in the properties of the macro constituents or the constituents, that is the fiber and the polymer. The third point is the uniformity of the properties in the bulk. In the bulk form the properties are different. So, that is another challenge. Fourth, adhesion efficiency is usually poor. Now, adhesion efficiency means that there are two important parts that go into making a composite. There are two important constituents that go into making a composite material. So, adhesion means how these will adhere to one another. So, adhesion efficiency means the bonding, or in the loose terms we can say it is the bonding efficiency, that how the fiber will bond with the matrix. If it bonds well, the resultant composite can take lot of load. If it does not bond well, the load taken by the composite would be comparatively less. So, we can say the adhesion efficiency is another issue. We have to see that how the fibers should be used, whether the fibers should be given some treatment when they are being put into the matrix, so that the bonding between the fiber and the matrix is good, or the adhesion efficiency between the fiber and the matrix is extremely high. So, the adhesion efficiency usually sometimes is poor, therefore, the resultant composite is not able to take a lot of load, is not able to bear the type of load that the composite has been designed for. The interfacial zone is prone to failure sometimes. Now, there is a matrix, there is a fiber, suppose this is a fiber, this is a matrix, and they have been combined together. The interface is the line between the fiber and the matrix. So, this particular interface sometimes may fail on loading. So, this is the interfacial zone which is prone to failure. If you remember, in the previous lectures on this particular module, we have seen that there is a matrix, there is a fiber and there is a thin line separating the fiber and the matrix, which is called the interface. So, adhesion efficiency is poor, interfacial zone is prone to failure. The tooling requirements are entirely different because some of the fibers like the glass fiber are abrasive in nature, and when they are flowing in the tool or when they are put in the tool, they are going to abrade the tool material. So, the tool, I mean to say the mold in which we are going to make the composite material. So, we will see what is a mold in the subsequent lectures. So, till today we can just take it as we can just call it as a mold tool. So, there is a mold tool in which we are putting our constituents, that is the fiber and the matrix. So, fibers being abrasive in nature may abrade the tool or the tool material. Therefore, that is another issue which has to be taken into account when we are thinking of designing a process to fabricate the or to process the polymer matrix composites. Then the next requirement is the processing methods are difficult to control and therefore they are costly. So, processing method, there are number of processing method, how they are classified that we are going to see, but there are few challenges in the control of these processing methods, because if you see in today's lecture, the very first slide we have seen, there is a fibrous reinforcement and there is a polymer. So, polymer has got some viscosity, so it will flow. So, when the polymer will flow, we have to convert that polymer into a solid product. So, that we will see in the subsequent slides that how that polymer which has got some viscosity is getting converted into a solid product, that we are going to see with the help of some processes, but we have to control the flow of the polymer and we have to incorporate the fibers in that flowing polymer. So, how to control this complete process is also a very big challenge. So, in order to summarize this slide, there are challenges in primary processing. Yes, tolerability, it is advantage in context of polymer matrix composite, but it is a big challenge when it comes to the processing of polymer matrix composite. In terms of materials aspect, tolerability is advantage. In terms of processing aspects, tolerability is a challenge. The two components, the fiber and the matrix, or the fiber and the polymer, have different properties. How to blend these two things together to make a composite material, that is a challenge. Non-uniformity of the properties in the bulk is another challenge. Adhesion efficiency between the fiber and the matrix can be poor, so that is another challenge. How to improve that adhesion efficiency? The interfacial zone between the fiber and the matrix is prone to failure. Most of the failures may take place at the interfacial zone, that is another challenge. Then the tooling requirements are different. The tooling requirements are not the same as that for metals. For composites, we have different types of tooling requirements. And finally, the processing methods are difficult to control. So, the summary says that yes, there are few challenges in context of the processing of polymer matrix composites, and which we have to address when we are discussing the various types or the various methods of processing the polymer matrix composites. Now, processing of composites, important issues to be considered while selecting any manufacturing process. So, when we are selecting any manufacturing process, because for composites or for polymer matrix composites, we will have a series of processes, or we will have a different types of processes which can be used to blend the two constituents together. Now, what are the two constituents? The two constituents are the fiber and the matrix. So, there are different processes which are used. So, how we are going to select, or what are the criteria, or what is the criteria which should be kept in mind when we are thinking of studying a particular process? First is the economic viability of the process, the second is the quality of product to be manufactured, and third is the technical versatility of the process. How versatile is the process? What are the different types of products it can process? What are the different types of volumes it can process? So, technical versatility, quality of the product to be manufactured, and economic viability of the process. Although the process is generating products of very high quality, but it on the other hand it is very costly, so that does not give a very economical product. So, economical viability of the process has to be good, quality of the product that is produced should be adequate or good, and the technical versatility of the process has to be considered when we are thinking of proposing certain methods for processing of polymer matrix composites. Last point gives the summary, the need of the hour. Today, when the polymer matrix composites are being used worldwide in different applications, the application spectrum has increased over the period of years. The need of the hour is the high quality. So, the quality of the product which we are making out of a polymer matrix composite should be good. The product should have a good quality and it should be cost effective manufacturing. The product cost should not be very high owing to the manufacturing. So, we have to think of manufacturing methods, we have to study, understand the manufacturing methods which should generate or which should produce the composite products which are low in cost. So, the need of the hour, just to summarize in single line, is the high quality cost effective manufacturing or high quality cost effective processing of polymer matrix composites. So, till now we have seen the materials aspect of polymer matrix composites and the slight you can say introduction towards the processing aspects. We have seen that what are the challenges in the processing of composite materials, and we have seen that what are the focus areas when we start our discussion on the processing of composites, that is the economic viability of the process, technical versatility of the process and the quality of the product produced. Now, processing techniques are different for different types of composites. Although the main important focus is same or the important focus is on high quality, cost effectiveness and technical versatility, but the processes which are used for processing the composites on the basis of the matrix material. If you see in this particular slide, we are only focusing on the matrix, the classification on the basis of the matrix material. The first one, the polymer matrix composites, the second one, the metal matrix composite, and third one, the ceramic matrix composite. So, the polymer matrix composite, ceramic matrix, metal matrix, the matrix is the catchword. So, on the basis of the matrix, we can have three different types of composites, and from the processing point of view, the processing terms, the processing requirements, the processing needs are different from all these three types of composites. So, our focus primarily would be on the polymer matrix composites in this particular module. So, here you can see the composites can be processed, we can have metal matrix composites, we can have ceramic matrix composites, but in this particular case or in this particular module, our focus is on polymer matrix composite. So, we would see different methods to process the polymer matrix composites. So, in the next lecture, our focus would be on certain techniques which would be used for processing the polymer matrix composites. More importantly, we would focus on one of the simplest and the most economical method of making the polymer matrix composite, that is the hand layup technique. So, just to summarize what we have covered in this particular lecture, we have covered the basic aspect of polymer matrix composite, what are the constituents that go into the polymer matrix composite, how the polymer matrix composites compare with the conventional materials, what are the challenges for the polymer matrix composites when they are proposed as the alternative material to the conventional material such as steel. We have seen what are the challenges in the processing of polymer matrix composites, and finally we have seen that the processes are different for metal matrix composites, ceramic matrix composites and polymer matrix composites. So, this particular module is focusing on the processing of polymer matrix composites, and in the subsequent lectures we would be focusing our attention on the various techniques which are used for processing of polymer matrix composites. Thank you.